Hi everyone, thank you for joining me today on this webinar. I'm Andy Shoemaker, the founder of NimbusDDOS, and today I'm going to perform a live DDoS attack scenario to illustrate how a traditional content delivery network provides incomplete protection against DDoS attacks. So before we start, I'd like to give you a little background on myself and NimbusDDOS. So prior to founding NimbusDDOS in 2013, I'd spent the last 15 years in the operations world primarily focused on massive scale consumer websites. As you might imagine from my list of past gigs, many of these were frequent targets of DDoS attacks, notably TripAdvisor.com and the online casino and poker company. I've also had a personal interest in DDoS attacks dating back to about 1995, when I first encountered the source code for a SYN flood attack on a security mailing list. Please take note of my contact information and feel free to reach out to me if you have any questions about this presentation or DDoS attacks. Also feel free to connect with me on LinkedIn if you use that platform. As for my company, NimbusDDOS is the industry leader in vendor-neutral DDoS attack preparedness services. Our vision is to provide the highest level of DDoS expertise to help our customers achieve the level of DDoS preparedness that their business demands. The foundation of our platform is the expertise of our DDoS engineers, all of which have firsthand experience with DDoS attacks. Additionally, all of our engineers have experience crafting DDoS source code in much the same way as a real attacker. Upon this foundation, we've built a handful of services that are shown on this slide. The first is our DDoS risk assessment. That's a DDoS-specific, non-intrusive reconnaissance of an environment intended to find the weaknesses before an attacker does. This is often the first step most organizations take in their path to DDoS preparedness. The risk assessment is often paired with our proprietary testing platform that allows us to launch legal and legitimate real-world DDoS attacks against an environment in a controlled manner. Our platform can do any of the attacks currently seen in the wild, including those of the Mirai botnet. We can launch attacks ranging in size from 1 megabit per second to well over 100 gigabits per second. Another service we offer are wargame or red team scenarios. These are designed to test response procedures of operations teams. NimbusDDOS engineers try to challenge the defenders with surprise attacks and dynamic attack vectors intended to push the response teams. Rounding out our preparedness package, we also offer formal DDoS training that can be customized for both technical and non-technical audiences. And lastly, we offer the industry's first and only DDoS preparedness certification. This is a certification framework created by NimbusDDOS to help companies evaluate their vendors and partners, or to provide a method to communicate their own preparedness status to their customers and partners. If you'd like to hear more details on any of these offerings, please feel free to contact me. So now with all of that sales stuff out of the way, let's dig into the tech stuff a little bit. The first thing I'd like to do talk about are the common strategies implemented by organizations during a DDoS emergency. So at NimbusDDOS, we're often tasked with helping organizations craft a cohesive and complete DDoS protection strategy. This often occurs after an organization has spent immense time and money cobbling together an ineffective solution. Generally, these solutions are implemented with minimal review during a crisis situation. So although they help in the short term, they may not be appropriate for the long-term protection of the environment. On this slide, I've listed a few of the common strategies that organizations use during an emergency. First, we see organizations attempting to use traditional network hardware like firewall and IDS devices. This approach is very limited since next-gen firewalls and IDS systems are not designed to protect against a DDoS attack. We routinely test customers with Palo Alto, Cisco, Juniper, Checkpoint, FortiGate, and other firewall products, and they don't even provide even a basic level of protection against DDoS attacks. Another common response in an emergency is the rapid deployment of a DDoS protection service. So this could be a service from any of the many DDoS mitigation companies out there. These services do generally work very well, each of which has their own pros and cons. But efficacy of these services aside, it's usually not good business to sign a contract for a service and implement a solution during a crisis. It usually costs more due to the crisis timeline, and it doesn't give you an opportunity to fully test the technology to verify that it's right for your business. So again, it may work in the short term for the crisis, but it may not give you a complete long-term solution to protect everything that you need. A third emergency response that we see is the outright black holing or null routing of IP address space during an attack. For those unfamiliar, this is when during an attack you have your upstream ISP discard the traffic destined for the IP that's being attacked. So let's say I have an IP address for my website and it's being attacked. So I call it my ISP and they basically drop all the traffic going to it. But another website that's on a different IP address will now work just fine. As you can probably imagine, this is a very, very blunt tool, and it results in both good and bad traffic being discarded. So although it's not an ideal solution, it's generally free to get your ISP to do this. And depending on the environment, the sacrifice of all traffic to one location may be worth it to save the remaining locations. The last item, which will be our main area of discussion today, is to hide behind a traditional content delivery network, or a CDN. This strategy is actually surprisingly effective, and even though today I'm going to poke some holes in it, I've used this approach myself during a crisis scenario. I've also written a couple blog articles many years back describing the basics of this strategy. In the next few slides, I'm going to show some high-level architecture diagrams that illustrate how a traditional CDN works and why it offers some level of DDoS protection. But then in our live attack, I'll show you how attackers can sneak through with some pretty obvious attacks. To get started, let's have a quick review of how a CDN operates. This slide shows the simplified architecture of a traditional CDN. Please note that for today's discussion, when I say CDN, I'll mean the traditional type that's meant to accelerate delivery of website resources by distributing and caching content throughout the world. There are CDNs that are purpose-built with certain security capabilities within them that sort of fall under a different category. And so I'll distinguish these from traditional CDNs by referring to those as security-enhanced CDNs. The majority of CDNs fall under this traditional type. Whereas most content security CDNs that are designed for security, those are a smaller number. So anyway, this is the simplified design of a traditional CDN. They basically operate as a massive, globally distributed cluster of web servers that cache content that originates on an organization's origin servers. Please note that a real-world CDN architecture is much more complex with multiple levels of caching, but for purposes of our demo today, this simplified topology will be fine. If we look at our client in San Diego, up in the top left here, we can see what happens when content is requested that the CDN already has cached. In this scenario, the client sends a request to the CDN, and the CDN answers directly without any communication to the organization's origin servers. Looking closely at the client in Boston, down the bottom left, we can see what happens when the CDN doesn't have the content in its cache. In this case, the client makes the request, and then the CDN must fetch that content from the origin servers. So, why do CDNs help with DDoS attacks? Well, it all boils down to scale. And for a CDN to properly operate in a normal condition, they must be massive, with resources distributed across the globe. This scale is what helps the organization in a DDoS attack. Along with that scale, in this specific slide, we see another reason CDNs help, and that's the caching I mentioned earlier. With many Layer 7 attacks, the web content being requested can be cached on the CDN vendor. As a result, no requests pass through to the origin, and it remains healthy and unaffected by the DDoS attack. So how else does a CDN help? Well, by design, CDN cache servers are located as closely to the end user populations as possible. This is done to speed up the delivery of content, but within the context of a DDoS attack, it can also help to isolate the effects of an attack. So in this slide, we have a scenario where a botnet that mostly consists of nodes located in APAC is hammering the CDN to the point that it's actually started to cause degradation. Now, naturally, the CDN operators will attempt to correct this problem by shedding load to other areas that are less heavily loaded. But that activity aside, if the botnet is primarily degrading the CDN in APAC, it means that customers located in the US won't be affected because the botnet isn't accessing those cache servers. And this behavior is not uncommon since many botnets do actually have a regional tendency or a regional element to their architecture. So let's look at a list of some attacks that will be blocked by a CDN. The main point of this list is that CDNs by default will protect an organization very well against volumetric and protocol attacks. There are literally thousands of DDoS attack vectors, but I want to list a few common attacks so you could all see how they stack up. Now, no service is bulletproof, and the one big caveat with this list is that the attack can't be so large that it actually impacts the entire CDN, or that it specifically exploits a weakness in that specific CDN. But for many of the common attacks like UDP floods and SYN floods, you should actually be in really good shape using a traditional CDN. When it comes to layer 7 attacks, the CDN can help depending on the attack vector. But as we'll see in subsequent slides, this is where the protection of a CDN starts to break down. One specific item I'll call out is that slow request and response attacks like Slowloris or similar vectors, those are mitigated very well by the CDN due to their massive size and their function as an intermediary proxy. All right, so let's see what isn't protected by a CDN. So the most obvious gap is that CDNs are specifically designed for the HTTP and HTTPS web protocols. Any applications that use a different protocol like SIP, SMTP, DNS, etc. can't be protected with a traditional CDN. Next, we have uncatchable content. On our original CDN architecture slide, you probably remember that we had our user in Boston who requested some uncached data. And for the CDN to process that request, it had to request that document from the origin server. The obvious question is, well, what happens with content that can't be cached, like dynamic data? It's simple, really. The CDN servers now become part of the DDoS attack by relaying through to the origin server. This is the area that in our live attack today, we will actually be exploiting. Our next gap is a direct attack on the origin servers. Earlier on, I referred to our protection strategy as hiding behind a CDN. That name is accurate because if an attacker is still able to locate and access the origin servers directly, they could launch a direct attack and bypass the CDN completely. So many people who use a CDN protection strategy attempt to address this by concealing the origins with network filters and the like. However, I'll note that my team routinely uncovers these origin servers as part of our DDoS risk assessment scans. So trying to hide them is often not terribly effective. I've also listed on this slide API endpoints as a weakness. This one is very similar to the uncatchable content, but I wanted to call it out specifically since public APIs are becoming more common and are very high-value targets for an attacker that can't be protected by a traditional CDN. And lastly, I just want to mention that even in a scenario where a CDN provider is able to mitigate an attack, you still may be on the hook with the CDN for paying a large usage fee for the added traffic. So although it's not terribly common, an attacker could perform an attack that is intentionally not aggressive enough to cause an outage, but is large enough to increase your monthly CDN bill by 10x. So although it's not an infrastructure DDoS, it does become a DDoS on your wallet. Okay, with that background info in place, let's meet the victim in our scenario today. So for this scenario, we have our test company, Widgets LLC. There isn't anything too remarkable about them. They're just a mid-sized company that sells widgets, and their website is their primary sales channel. So for those who have perhaps attended some of our previous webinars, this should look very familiar, but we will have some new changes, so please stick around. Oops, I jumped ahead. So the technology stack of our company is also not terribly remarkable. They're hosted in Amazon Web Services and have a modestly sized origin web server positioned behind the CloudFront CDN. So for those that are unfamiliar with Amazon CloudFront, CloudFront is their traditional CDN product. And also I'd like to take a quick moment today to mention that although I'll be using AWS in our scenario today, the behavior you will see is common of all traditional CDN providers. And I'm not in any way suggesting that Amazon's CDN is deficient. It's actually a very good product for a traditional CDN. So additionally, to protect themselves against threats, our victim company has taken steps common in the industry, including running periodic vulnerability scans and having software patch procedures and the like. And of course, they've also heard from people that they don't really have to worry about DDoS inside of Amazon because Amazon is so large. So let's take a quick look at the widgets website. As you can see, we have a very simple placeholder website. It's just some static content. Now let's go ahead and meet our attacker. Now, attackers can range in capabilities from a single lone wolf on one end of the spectrum to organized crime or even nations at the other end. In this example, our attacker is a lone wolf who makes money from extorting people with DDoS attacks, and he protects himself by using Bitcoin to hide the transfer of money. Now, much like the Widgets LLC, our attacker's capabilities are also fairly modest, with a very small botnet of just 5 nodes. Now, with such a small botnet, he can only launch small attacks of perhaps a few gigabits per second. So for our attacker to be effective, he'll need to find a particularly weak area to exploit. Now, with regard to size, to get a sense of scale, consider that the Mirai botnet attacks in 2016 launched DDoS attacks using around 500,000 nodes. And in 2016, there was also an attack that exceeded 1 terabit per second. Now in a moment, I'm going to walk through a live demo of 2 DDoS attacks. Both attacks will target the widgets.nimbusDDOS.com website that is hosted on the CDN. And they're basically going to be nearly identical in most respects. The major difference is that the second attack will attempt to circumvent the CDN to directly target the origin by requesting random documents. Since these documents aren't cached in the CDN, the requests should pass through to the origin, resulting in a performance degradation. So now let's begin. So before we launch our attack, let's review the current status of the target. So in our web browser, we can very quickly we can go to our widgets website, and we can very quickly reload that website, and you can see that the page loads very quickly and without any errors. If we switch to our terminal window, in this window in the top right, that's my local laptop. If I try to load the site using the curl command line tool, we can again see that the site is going to load fairly rapidly and without any errors. So if I run that, we can see that it's about 66 milliseconds. If we run that a few times, 76, so forth. And then for this scenario, I've also decided to leave the origin servers accessible just to help us measure the effects of the attack. It's worth noting that although it's not required, origin servers are often left accessible from the internet, which is certainly a topic for a different webinar on a different day. But as you can see, the request to the origin server, so origin.widgets.nimbusddos.com, those also complete fairly quickly and load normally. And again, if I go back to my terminal window and I load the origin site, so here's my origin site using curl. We can see again that the site loads rapidly and without any errors. So it's a little bit slower, 394 milliseconds, 212 milliseconds, so forth. But it still loads successfully. It is worth noting that in the website, I've added a timestamp at the end that is being continually updated on the origin servers. So you see this timestamp right at the very end. And you can see that when I load the site from the origin, the timestamp is constantly changing. So every second, basically, it changes. And then when I load the CDN version of the site, so if I don't go to the origin, but I go to the CDN version, you'll see that it doesn't update very frequently, but it's still basically up to date. This will actually update about every 30 seconds when the content expires on the CDN. I'll explain why we did this later on, but I basically added this timestamp just to help illustrate, how the behavior of the attack presents itself. So now let's go ahead and start the first attack. As I mentioned before this, this is basically going to be an HTTP GET request flood that's sending traffic to widgets.nimbusddos.com. So this traffic is going to the CDN and not to the origin servers directly. So I'm going to run this command on our 5 attack nodes. So in this window, this is all of our attack nodes. And now with the attack started, let's take a look at the logs on the origin server to see what's happening. So down here in this bottom window, this is my target server. I'm just going to look at the log file, and you can see that there's some recent entries in here from 1842, which is just a minute ago. And if we wait, we can see a few more entries trickle in. So as you can see, CloudFront is accessing the origin server. So that came from CloudFront, but the request rate is actually very low. Just a couple entries in the last minute. So let's try to load the site and see what happens. So first, let's look at the command line tools. So I'm going to go back over to my laptop window in the top right, and I'm just going to run the same commands as before. So this first one is going to load the main landing page on the CDN. So we're just going directly to the CDN. And that first one took a little bit of time, but any subsequent request seems to be loading very quickly. 66 milliseconds, 74 milliseconds. And as you can see, it loads definitely in a timely manner still. And you can also see that the timestamp at the bottom is also fairly up to date. So it shows the time as 18:43:56, which is less than a minute ago. And if I do the same command, but directly loading the site from the origin server, so I'll run my command against the origin. So here we have the origin server. Again, we see that it loads normally as well. And you can also see that the timestamp is, again, also being updated in a timely manner. And lastly, if we look at our browser window, everything here also still loads properly, as you might expect. So we can load that a couple times. That seems to work. Go to the origin site, load that a couple times. That one works as well. So this first attack seems to have really had no impact on the target whatsoever. So let's go ahead and shut that down. So with the initial attack failing, it looks like our attacker is going to need to be a little more clever with their second attempt. Now, on a side note, a failure like this is actually not uncommon for attackers. You might imagine that companies with large amounts of load-balanced resources and significant caching can handle a massive amount of requests. So attackers often focus their attacks on areas that are likely to pass through caches or otherwise cause stress to the environment. So let's do a little bit more digging into our target site. First, let's just take a quick look at the DNS for our target. So we'll just do an NS lookup just to understand a little bit more about how our site's set up. So here, by simply looking at the results of a DNS query, our attacker can easily identify that a CDN is in use. And that the reason his attack failed is likely due to the CDN absorbing the requests as part of its caching. But our attacker can circumvent this with an easy trick. So this second attack is going to be an HTTP GET request flood, nearly identical to the last attack. Unlike our previous attack, this one will be requesting random, non-existent documents rather than the default landing page. Now, by doing this, the attacker is guaranteed that his request won't be cached in the CDN and will pass through to the origin server. So let me just start that up. All right, so that is started on our 5 attack nodes. So with the attack started, let's take a look at the logs on the origin server down in the bottom to see what's happening on our target. So I'm just going to look at the last 50 requests to the server. Aha, and you can see that we have all of these requests coming from CloudFront that are for all of these different random URLs. And if we run that a few times, we can see that there's just a ton of them coming in, literally thousands per second coming in. So let's try to load the site now and see what happens. So first, let's take a look at those command line tools again. So we'll just run the same command as before. So this first command is attempting to load the site directly from the origin server. So again, just doing it from the origin. And if I hit return there, we can see it just kind of sits there. We'll just give it a few seconds. If we waited long enough, eventually we would get a timeout error message. But the point being, it's obviously not performing as fast as it was before. And of course, a customer is eventually just going to give up. So I'm going to go ahead and cancel that request as well after 22 seconds of it not loading. And if we do that a few more times, we can see that, again, 7 seconds. Eventually, I just canceled it a few more times. So you can basically see that, we have a significant failure rate. It appears to be 100% of requests are failing. Now, if I do the same command, but against the CDN URL, so let me go to my other command. So we're just going to hit the CDN URL. We'll see something that's actually a little bit interesting. So this one, just like the other one, it will take a moment. In this case, I'm actually not going to cancel it. I'm going to let it actually run to completion, because what we're going to see is we will get a response eventually, and that's sort of the interesting part. So it sits there. All right, there. After 21 seconds, eventually we got a response. Now, if I run it again, 248 milliseconds. So, 90 milliseconds, 71 milliseconds. So now it's actually performing very quickly. So, it does load after that initial extended delay, but the reality is that this is just the tip of the iceberg. So behind the scenes, the CDN is actually unable to contact the origin server, which means that uncached data will never load. So if I now request, some random document, so I'm just going to throw on some random URL here. You can see that it doesn't load. So let's just wait a moment. We'll actually get an error message. So after 16 seconds, we got this error message from CloudFront saying that it was unable to talk to the origin server. So any uncached data will get this error message. And if we're requesting data that was previously cached, like the main website, that one loads. But if we look at the timestamp, you can see that the timestamp is actually outdated. So this is old content. So this content hasn't been updated for 8 minutes. So it hasn't been updated since we started the attack. So you can see that that's going to present a bit of a problem if you have dynamic data. So it's worth noting that the behavior of the CDN when the origin is unreachable is dependent upon the CDN vendor. So some vendors like Amazon, they will serve up the old content, whereas many other CDNs will simply produce an error message indicating that the origin server is unreachable. I think in either scenario, this would be a significant outage to just about any business out there. So in most cases, expired data is not very useful either. So in the second scenario, the attacker was able to slightly modify their attack to cause a DDoS attack. Again, a resource that companies thought were protected by the CDN. So I'm just going to go ahead and shut down the attack really quickly here before we proceed. So what caused this behavior? In our demo environment today, the origin site is partially protected by the CDN that sits in front of it. The CDN is good at absorbing certain types of attacks, but not others. In the first attack, we simply requested the main website repeatedly, which was quickly served up by the CDN, never touching the origin servers. Now in our second attack, we forced the CDN to participate in our attack. So by requesting random URLs that we know won't be cached by the CDN, by its very nature, if a CDN doesn't have a requested document, it will attempt to retrieve that document from the origin. So the CDN server will now bombard the origin server with attack traffic on behalf of the attacker. And I do want to mention also that there are numerous methods that attackers can use to circumvent a CDN. And the method that we use today is really just one of many. So what does a security-enhanced CDN look like? So let's go back to our slide deck. So a security-enhanced CDN is basically a CDN that has built-in security features to protect customers against a DDoS attack and other security risks. On this slide, I have a very simple diagram that illustrates how a filtering layer in a CDN network can help protect customers against attacks. They can protect their origin servers. Now, in a real-world environment, the security-enhanced CDN would have multiple layers of protection. But the point is that the CDN is actively detecting and blocking bad traffic before it passes to the origin server. Now, with our demo complete, we're actually now going to have a Q&A session. So I want to thank everyone for attending. And by all means, if you have any questions about DDoS attacks or any questions about this slide deck or the demo that we did today, please feel free to reach out to me. Again, my phone number and my email address are here, as well as my LinkedIn user ID if you'd like to connect in LinkedIn. Thank you, everyone.